Okay, we can go ahead and start. Good morning or good afternoon, everyone, depending on where you are. Welcome to the Western Session 8, Public Transit Planning and Operations. My name is Ali Reza Khani. I'm a professor at the University of Minnesota, Twin Cities, and I'm chairing the session. And I'm being assisted by Anandia from University of Arkansas, who provides technical assistance. Excuse me. So we have six very interesting presentation on public transit, different aspects of public transit planning operations. We have 2 hours for this session, and we aim to finish about 5 to 10 minutes early. And if we get a chance, maybe halfway in the session, we can take a 5 minute break. So we might have three presentations, 5 minute break. If you have time, come back for the other three presentations and finish 5 to 10 minutes before 1 p.m. So everyone gets prepared for the next session. And then each presenter has 15 minutes, up to 15 minutes. Feel free to use less time, wrap it up early if you can, but 15 minutes is the maximum that we have. At 15-minute mark, I may have to stop you, and then we transition to questions and answers. If we go beyond 15 minutes, we may have to skip the Q&A. So again, I would appreciate presenters if they can manage their time. And if you can have your chat box open, if it doesn't confuse you, if it's convenient for you, if you have it, can have it on the side of your screen. We might give you cues when there is 5 minutes or 1 minute left. Don't worry about it if it confuses you, but we provide that for convenience. I guess that's it, Anandia. If there's anything else, let me know. Otherwise, we can go ahead and start with the first presentation. I make an introduction. Tianjia Yang, if you want to go ahead and share your screen. Tianjia is a postdoctoral scholar in civil and environmental engineering at the Pennsylvania State University. His research interests include intelligent transportation systems, connected and autonomous vehicles, traffic flow theory, machine learning, and operations research. Please join me in welcoming Tianjia for the presentation. Go ahead.
Thank you for having me here. So can you see my screen?
Yes, all good. Go ahead.
Okay, so today my topic is about how to use multi-agent reinforcement learning to improve the transit efficiency along the corridor. And transit singular priority, I think, is microscopic level idea among the transit priority umbrella, and we try to adjust the transit signal control timing and phase to give priority to buses that pass the intersection. So traditional TSP control generally cause adverse effect to other traffic because you see the green time duration is limited resource, and different traffic compete for this resource. And right now, because there's many new technologies that we can use, especially for like connected vehicle technology, which can provide richer real-time data for the traffic environment, and also we can leverage the rapid advancement of AI technology, building smarter singular controllers. So we think there's a great potential to advance the transit singular priority research. And here this research is try to develop a multimodal singular control framework that can use the connected vehicle data and use the multi-agent reinforcement learning to optimize both the performance of transit vehicle and also the private vehicle, and at least can balance their performance. So first, I'd like to briefly introduce what is multi-agent reinforcement learning. So reinforcement learning, typically reinforcement learning is try to optimize the agent action based on the environment, based on the interaction with the environment. So for a single agent, they observe the surrounding information, and based on the surrounding information and based on the own policy. Here, I'd say the policy is just a control logic, and based on the own control logic, they provide action, and the action will feedback or will change the environment to a new state. And during those interactions, the agents continuously refine their own policy to achieve optimized certain goal. And the reward is defined by ourselves to let the agent to achieve certain goals. But for multi-agent system, we have more than one agent, so they may have some conflict when they provide actions. So we have to try to figure out how to coordinate those agents based on the multi-agent system, based on like maybe Gale theory. And here we use a different training process. And here we have for typical reinforcement learning application, because we don't try to refine the backbone algorithm. We just try to apply the reinforcement learning to our specific problems. So we have to carefully define the state, the local observation, and the action, and also the reward function to help us to solve the problem. So here, because we try to optimize the traffic signal, we try to optimize the efficiency along the corridor. And there's multiple intersections along the corridor, and within each intersection there's a traffic signal controller, and each controller we can think is the agent, and the agent perceives the surrounding information, and here we just because we rely on the connected vehicle technology, we just take the 350 meters of the approaching lane and cut every incoming lane into 7 meter cells, and then for each lane there's about 50 cells, and combine all those cells, we have a table for the surrounding intersections, and we fill those table with two values. The one is about the speed of each connected vehicle, and the second is the occupancy of each connected vehicle. And based on these two tables, we can also obtain the position of each vehicle. And because this table is just like an image like representation, we can then process by the convolutional neural network to extract those features. And for the global state, we combine all the local observations, and also we add the phase state of each agent together. And for the action space, traditionally we use the first, which is discrete action space. So for a typical four-leg intersection, we have 8 possible phases. So the first discrete action space is just the 8 different phases. So at each decision step, we decide the next phase. So if the next phase is the same as the current phase, we continue this phase. But if the phase is different from current phase, we transition from current phase to the next phase. Also, the transition process has yellow time and all red time. And for the multi-discrete action space, it's a bit like how we conduct in our real world. We change the phase time, and also we decide the green time of next phase. So here the multi-discrete action space has 2 components. The first is the phase with the 8 phases, and the second is the corresponding green time of each phases of each phase. So in this way, we can at each decision step we can decide the next phase, and also the green time of the next phase. So it will reduce the decision frequency significantly. And for the reward function, it is the differences. We define the differences in the cumulative person delay. So we times each vehicle delay with the corresponding occupancy. So in this way, if the typically bus will have more passengers on board, and the occupancy acts like the weight of the delay. So with more passengers on board, the vehicle will gain more weight on the reward and in this way the outcome will favor more transit vehicle than private vehicle, and in this way it also provides conditional priority to buses with more passengers on board. And for the training process, we use centralized, because it's a multi-agent system, we use a centralized training and decentralized execution framework. So we use PPO, which is stands for proximal policy optimization. So for it's a classical reinforcement learning algorithm, and it has two types of neural network. The one is critical network, and the other is actor network. And for the critical network, it is used to guide the actor network for the policy update. So we can use for the centralized critical, its input is the global state and the reward for all the agents. And based on the big picture, they can guide each agent. They can guide the policy of each agent. So during training, we can coordinate the policy for each agent. But after training, during the execution, the centralized critical network can be discarded, and each agent observe the local observation and provide their own action to the so each just like each single controller just control its own actions. And to evaluate the performance of the proposed framework, we built two corridors. The one is hypothetical corridor. So it's the distance between each intersection is fixed, and the traffic demand is also symmetric. And we also based on the real world condition to build a real world corridor. So you can see for this corridor, we have not only have a typical four-leg intersection, we also have one T-shaped intersection, and the traffic demand from different approach is very different. So it's highly heterogeneous. And we also compare the proposed framework with different controllers, like the real-time signal control, which is widely used in the real world, and fully actuated singular control. And we also compared with several self-organized control methods like max pressure singular control and the longest queue first singular control. And we also trained three different agents. The first is independent PPO. So for this, we did not use centralized critical network. We just trained we just let each agent act by themselves. And the second is multi-agent PPO, which use discrete action space. And the third is multi-agent PPO with the multi-discrete action space. So the figure in the right is the training process, and we can see that for the IPPO, which the trained independently, their performance is very unstable, and especially for the peak high traffic demand scenarios. And for the MAPPO and MAPPOM, their performance is much better. And here is the performance in terms of the bus average delay and the car average delay. So we plot this figure to show the overall performance, the balance of overall traffic performance. So the horizontal is the car average delay, and the vertical is the bus average delay. So in the hypothetical scenarios, the MAPPOM performance provides the best balanced performance in terms of both bus average delay and the car average delay. And in the real world scenarios, because the things get complicated, the MAPPOM gets a bit struggle, but I think but I think it also provides decent performance in terms of both the two delays. And we also conduct sensitivity analysis among several critical factors. The most important is the connected vehicle maximum penetration rate. You see, we rely on the observation rely on the available of the connected vehicles available connected vehicle information. So with less connected vehicle on the road, we can the performance decrease a lot. But by using the multi-agent multi-discrete action space, the performance became better compared to just use the traditional discrete action space. And we also change the passing accuracy to see how it affects the performance. And as the passenger occupancy increase, the bus average delay decrease, but the average car delay did not affect a lot. And we also changed the arrival headway, and it turns out it did not affect much about the average bus delay, but it can improve the overall traffic delay because there's less bus travel on the road. So the takeaway is that multi-discrete action space show more potential to for the deployment, and we can still provide priority with less impact on the cost, and we can consider use based on the priority, based on the onboard passenger in terms of different vehicles. So the constraint is just the collective penetration rate. And thank you.
Thank you. Perfect timing and very good presentation. The audience, please type your questions in the chat box. I have one question, and this is a very simple question. Maybe you explained it, but on the graph that you showed the performance, maybe this is the key point of your presentation. So it shows that the delay is reduced both for vehicles, private vehicles and buses. I think this is a little surprising in a good way. You would usually expect that you have some sort of trade-off between buses getting priority and getting improved travel time, or all other vehicles. Can you comment on that a little bit about how realistic this is if it's implemented in the field?
Yeah. So I think for the traditional ways, or for example, the pre-timed control, we use based on the historical static demand to optimize the traffic demand, to optimize the single plan. So when the real-time traffic is fluctuates a lot, so its performance degrades. And for the fully actuate single control, I think they can adjust the single timing and phase in real time. So its performance sometimes is really quite well, I'd say. But because it's still short-sighted, myopic, because they did not consider the future. So their performance is still there's still space for improvement, I say.
Okay, thank you. Last call for any other questions. I'm not seeing anything in the chat box. So in the interest of time, we are going to transition to the next presentation. Thank you, Tianjia.
My pleasure.
And the next presenter is Golbarg Dokhani. Golbarg, if you can go ahead and share your slides. Okay. Golbarg is a PhD student at the University of Michigan, Ann Arbor. Her research focuses on transportation systems with interest in optimization, reinforcement learning, and intelligent mobility. She holds a bachelor's degree in industrial engineering with minor in computer science from Sharif University of Technology. Golbarg, go ahead.
Hi everyone, can you see my screen?
Yes, if you can make it full screen, that would be great.
Is that okay?
Yes, perfect. Thank you.
Great. Today I'm gonna present present our work on a Bayesian-guided aggregation-disaggregation algorithm for transit planning. The main goal of this work is to design detailed transit systems and rider assignments while also addressing the computational challenges that arise when we want to model transit system at a high level of detail. Our motivation for this work is that public transit systems plays an important role, especially for those people who do not have access to private cars. And this even becomes more difficult in small and low-density communities when demand is often spread across regions. So it is hard to design routes that can efficiently serve everyone. Transit systems, transit agencies may not necessarily have lots of vehicles and may not be able to offer frequent services. Another important point is that serving a rider is an individual feasibility problem. A rider can be served if the vehicle routes, schedules, and available capacity, riders' time windows, and transfer opportunities all work together. So effective transit planning is very important, and we want to use these limited resources carefully to design a system so that it can provide the greatest possible benefit to both riders and operators. Transit planning involves several connected challenges. From the operator's side, we need to decide about vehicle routes, schedules, and capacity usage. From the rider side, we need to decide, we need to care about rider quality, the trips quality. And these decisions are strongly connected with each other. So another major challenge is scalability. If we present all these details explicitly, the optimization problem becomes very large. So our main question is that how can we preserve this detailed rider vehicle matching while avoiding full-scale problem directly? To answer this question, our approach has three main components. First, we develop many-to-many optimization model that jointly decides about vehicle routes, schedules, rider assignments, transfers, and capacity usage. To make the problem scalable, we use an aggregation-disaggregation approach, and we solve the many-to-many model on the coarsened graph of the network. And the third component is the extension of Bayesian optimization. We use the Bayesian optimization to intelligently search for good network aggregation instead of just doing this blindly. This work has three main contributions. The first contribution is the unified many-to-many formulation. Instead of considering vehicle routing, rider assignment, and transfer separately, we model them together at the level of individual riders and vehicles. This level of detail is important because whether a rider can be served depends on several things at the same time. And the second contribution is our aggregation-disaggregation framework, which allows us to preserve the detailed model while reducing the computational burden. And the third contribution is the extension of Bayesian optimization to a combinatorial clustering space. And also we adopt a similarity metric that is specifically designed to compare aggregation configurations. Now I will explain the many-to-many optimization model, and I will call this M2M model for the rest of the lecture. This model inputs are zones, demand, vehicle capacity, and riders' time windows. This model makes a decision about vehicle routes, schedules, riders' assignments, and transfers. The main objective is to serve as many riders as possible, while also maintaining acceptable service quality. We consider an offline planning setting. Rider demand is known and accurately forecasted before we run this model, and travel times are deterministic. We also assume riders arrive at their boarding stations based on the planned schedule. And yeah, this is the formulation of many-to-many optimization. Each passenger can be served by many vehicles. Each vehicle can serve many riders, and that's why we call it many-to-many. In this model, the objective tries to maximize the number of served riders while considering a small penalty for service quality. This quality is defined with the ratio of riders' actual transit time divided by riders' shortest path travel time. And constraints make sure that routes of vehicles and riders are continuous, they're feasible, and the number of transfers are limited. And the reason we choose this individual level formulation is that the aggregate model may tell us how much demand is served, but it may not tell us whether a specific rider actually has a feasible itinerary. This slide shows the overall solution framework. Our solution framework is an iterative process. We first generate a pool of possible network aggregations. We evaluate a small number of them to train the surrogate model in the Bayesian optimization. And then for each selected aggregation configuration, we execute the M2M disaggregation pipeline. First, we solve the M2M model on the quiescent time-expanded graph of the network, and then we translate the solutions back to the original network, and then we have the post-disaggregation rider assignment step. At the end of this blue pipeline that you can see in the picture, we obtain a performance score for that aggregation. We use this new observation to train our Bayesian optimization. And in the Bayesian optimization, the acquisition function, which is the expected improvement, tries to select the next aggregation, which is more promising to evaluate. And then we do the same process for the next aggregation. And this process continues until we reach to the evaluation budget. So I'm gonna go into more details. As I said, we first start with a pool of candidate aggregations, and we use a small number of them to train the Gaussian process within the Bayesian optimization. In the aggregation step, we keep depot zones separate, separate clusters because they kind of play an important operational role. And for aggregation, we use k-means algorithm, and each cluster also has a separate hub. We try to estimate travel times between clusters conservatively because we want to give enough time for the vehicle movement so that when we later want to translate solutions back to the original network, it can still be feasible and implementable. Then we solve the M2M model over the coercent graph. And the next step is the disaggregation step. In this step, we translate the solution back to the original network. This step has two main parts. First, every vehicle movement between two clusters is translated into an actual route on the original network. Then within each cluster, we also make sure that vehicle route remains feasible with respect to vehicle capacity. After disaggregation step, we have another optimization step, which is called post-disaggregation rider assignment. Here, the routes are fixed, and we focus on the best detailed rider assignment on those routes. This step is needed because some riders may appear unserviceable, even though after we restore the detailed network. So there might be actually enough capacity to serve them. And this disaggregation model can reveal new service opportunities for us. And the next step is Bayesian optimization. The search space here is a pool of candidate aggregations. And since the M2M disaggregation pipeline is computationally expensive, we use the surrogate model for the distance metric in the kernel of the surrogate model. We use rand index. For every pair of zones, we compare two aggregations. And we call the agreement as we call a pair of zones as an agreement if two zones are in the same cluster in both aggregations, or if they are not in the same cluster in both aggregations. Then we used expected improvement as an acquisition function of the Bayesian optimization. Now I will move to our case study. We used Benton Harbor as our case study. This network includes 69 zones. We used 106 demand over 60-minute planning horizon. We have two vehicles with the capacity of 30. To evaluate the benefit of performance-guided aggregation-disaggregation, we compare the Bayesian optimization with random selection. We use the same candidate aggregation pool and the same initial configuration for both methodologies. And as you can see, Bayesian optimization finds better solution much faster. And we can say that it is more sample efficient. Here, this figures looks the same experiment from another perspective. Instead of asking what solution quality we have at each iteration, we ask how many required evaluations we need to reach a certain matching rate threshold. On the x-axis, you can see the M2M disaggregation matching rate threshold, and on the y-axis, you can see number of iterations required to reach to that threshold. And as you can see, if we ask for higher quality solutions, the gap between Bayesian optimization and random selection becomes larger. And BO also has lower variability, and it means it gives us good solutions more consistently across different runs. Here, I have a table to compare our Bayesian-guided methodology with directly solving the full resolution of many-to-many model. For this experiment, we consider 5 demand scales from 0.6 to 0.8 to 1.4, and for every scale, we run Bayesian optimization 10 times, and we then give the commercial solver the same amount of computational time as the corresponding Bayesian optimization run. And as you can see, for example, for the demand scale of 1, the average Bayesian optimization result is about 66%, while the direct solver produces no solution within the L of time. So it shows that aggregation makes it possible to obtain useful and consistent solutions in cases even the direct solving of the full resolution model with the solver is kind of impossible.
Thank you, Golbarg. I have to stop you if there is.
Thank
Okay,
you.
great. Perfect timing. So yes, we are past 15 minutes. We are about at 16 minutes. So there is time for one quick question. I don't see anything in the chat. I would like to ask the audience again, if you have any questions, please type it in the chat. I asked one quick question. You talked about the scalability, and your case studies showed 2, 3, 4 vehicles. Maybe I missed that when you explained it, but do you think your framework is applicable to large transit network like those in New York City, San Francisco, that scale of transit systems?
I agree that the case study may seem small, but the many-to-many optimization model is built on the time expanded network. So the number of decision variables in that model and number of constraints depends on the number of vehicles and number of riders and the number of links of the time expanded network interactions. So the problem is very large in terms of modeling. Yeah.
Yes, absolutely. Thank you. Yeah, transit network design, very difficult problem. But thank you very much, Golbarg.
Thank you for having me. And
yeah, of course. Thank you. Next presentation is by Ritun Saha. Ritun is a fourth-year PhD student at the University of California, Irvine. Ritun's research focuses on developing strategies for the optimal integration of microtransit and fixed-route transit, stochastic modeling of operational uncertainties in shared mobility simulation, and developing optimal ride matching policy under uncertain operational conditions for shared mobility systems. Ritun, go ahead. You are muted, but we can see your screen. Great.
Can you see my screen? Hi.
Yes.
Okay. So our study is titled as Optimal Fare Policy and System Design for Integrated Fixed Route Transit and Microtransit Systems. First of all, Microtransit is an on-demand ride pooling service, much like Uber Share or Lyft Line, but the difference is being that it is highly subsidized, so fares are low, but the wait times are longer, and usually the fleet size is inelastic. Now, microtransit system being an on-demand system, it has the benefits of route and schedule flexibility, whereas fixed route transit has the benefit of capacity. And if we put them together, then they can fill the service gaps, which is usually left by fixed route transit. And also we can expand our transit service coverages in low demand region, and also where the fixed route transit is sparse. In this study, we solved an optimal fare structure and system design problem for integrated systems like this, which would benefit the travelers and transit agencies at the same time. And from these optimal design configurations, we provide policy relevant insights. Through our modeling approach, we capture the intertransit mode path which a heterogeneous traveler can take while taking the integrated transit service. And also we consider two critically important objective and the trade-off between them, which is minimizing taxpayer subsidy and maximizing regional mobility. We consider a diverse set of differential fares also, which is usually not covered in current literature, and also not very much used in the current services. They are distance-based fare, peak period surge factor, and intermodal transfer discount. We formulated our problem as a bi-level problem. On the upper level, we use a multi-objective optimization, which essentially models the transit agency taking the decision about setting fares and setting the frequency and the fleet size of the system. And on the lower level, we have a multimodal transportation system model, which essentially calculates the performance metrics corresponding to the decisions about the fares and the system configurations. So the multi-objective optimization problem simultaneously considers two objectives, that is minimizing the subsidy and maximizing the mobility benefits. We consider decision variables such as the fares, that is FRT fare, microtransit fleet size, microtransit start fare, and distance-based fare, then peak period surge factor, and the intermodal transfer discount, and the headway for fixed route transit. Transit subsidy is the difference between operating cost and revenue. Operating cost comes from the labor cost for fixed route transit and microtransit, and per mile gasoline cost for FRT and microtransit. And the revenue comes from the fare for fixed route transit and microtransit. The mobility improvement for a particular rider is quantified using the difference between the log sum of the after introducing microtransit compared to where the microtransit was not there. And if we sum this up over all the riders in a particular region, then we get the overall mobility improvement after introducing microtransit. The multimodal transportation system model uses two set of parameters. The fixed set of inputs include the travelers, the roadway network, the walk network, and the fixed route transit network, whereas the variable set of inputs consider all the decision variables that we use in our optimization model. The multimodal transportation system model includes one mode choice model, which calculates the travelers and the mode shares between the two modal choices, that is the integrated transit system and the car mode. So the utility equations consider all the possible parameters like walk time, in-vehicle travel time, wait time for microtransit, fixed route transit, then all the fare parameters, number of transfers that a passenger might make, and also the rejection penalty for microtransit. Similarly, for auto mode, we consider the in-vehicle travel time and the operating cost. The utility term, the deterministic utility term, can be calculated by finding a generalized cost shortest path through the multimodal network consisting of fixed route transit, walking network, and the microtransit network. We can see a typical path in this figure where the age weights include all these parameters that we consider in this equation, and finding the total cost provides the deterministic term. And we do the same for the auto network as well. We solved an iterative mode choice convergence problem, and upon convergence, we calculate the performance metrics that we need from this model. We use multi-objective Bayesian optimization because the two objectives that I explained are black box objectives because they require running a simulation model, and also they are computationally expensive to evaluate. That's why we use Bayesian optimization. Our case study areas are Lemon Grove and downtown San Diego. In Lemon Grove, which is a low demand suburban area having 6 number of transit lines, and downtown San Diego, which is a high demand area having 20 number of transit lines. And currently, both of these areas do not have microtransit service. We used Sandags transit and road network for our network construction. We generated our demand data from activity sim. We generated 15,000 trips for Lemon Grove and 45,000 trips for downtown San Diego. Our assumptions are that the current FRT only system that exists in both of these regions have $2.5 flat FRT fare and 20-minute headway for all the routes. Then microtransit vehicles can pick up from 75% of the street corners. Our analysis period is from 5 a.m. to 8 p.m. And additionally, we consider that downtown San Diego region has a parking price of $2 and $1 per hour for peak and off-peak periods. This is the result for Lemon Grove region. The pink dots represent the Pareto optimal frontier for the optimal designs. On the x-axis, we have the first objective, that is the total subsidy delta. That means what is the increase in subsidy after we introduce the integrated system compared to the currently existing baseline FRT-only system. And on the y-axis, we can see that corresponding mobility improvement that the subsidy provides. First, with subsidy increase, the mobility improvement increase sharply. Then it flattens out a little bit. And the green dot represents some designs where we kept the FRT fare at $2 and we use microtransit fare $1 flat, but we do not use any differential fare components. And we show that the corresponding mobility improvement and subsidy requirement are suboptimal. That means they sit below the Pareto frontier. That means they are either harming the community mobility or the transit budget. The highest mobility solution, improvement solution requires a 7-vehicle microtransit fleet, and the lowest one requires a 2-vehicle microtransit fleet. Also, the highest mobility improvement requires the highest subsidy investment, and the lowest mobility improvement requires the lowest subsidy investment. The highest mobility improvement solutions usually have higher fare components compared to the lower mobility improvement solution. In downtown San Diego, the pattern is quite different. We can see that the Pareto frontier starts from the negative side of the subsidy improvement. That means for a number of solutions, after introducing the integrated transit system, actually lowered the subsidy requirement compared to the baseline fixed route transit only system. These are the full set of optimal designs for Lemon Grove region. We have 23 designs, and these are the full set of optimal solutions for downtown San Diego regions. We have 34 designs. From the results, we can see that subsidy and mobility improvement both strongly depends on the fleet size. As we increase the fleet size, we can get reduced wait time and more mobility improvement. But as we go on increasing the fleet size, the benefits on mobility improvement starts to diminish. So we recommend that we need strategic fleet sizing, considering the trade-off between the objectives such as subsidy requirement and mobility improvement, rather than just blindly expanding the fleet. In downtown San Diego region, we see that even introducing a two-vehicle microtransit fleet along with the fixed route transit can bring down the subsidy improvement by as much as $960. Also in downtown San Diego region, we see that the peak period search factor often reaches to a value of 4 compared to the Lemon Grove region, which is within 1 to 1.5. This is required because downtown San Diego region has a high demand, and a high surge factor helps in managing the demand during the peak period, especially, and also it keeps the microtransit wait times within a serviceable limit. And from the results, we see that our optimal solutions keep it within 10 minutes in downtown San Diego. We understand that public agencies are less likely to implement these such factors, but our solutions show that they can help attain optimal outcomes. In Lemon Grove, optimal solutions often use high transfer discounts compared to San Diego, where we do not see much of a transfer discount, intermodal transfer discount. That is because in Lemon Grove the demand is low, and also the fixed route transit coverage is less. So providing a high transfer discount actually motivates community member to take transit, and it also helps the transit agency in terms of subsidy requirement. And in downtown San Diego, where we have high demand and also well supplied fixed route transit, so we do not need as much as transit discount. Then in downtown San Diego, we see that many optimal designs use $1 fixed route transit fare and a very frequent service that is 10 to 12 minutes compared to the baseline service that we considered with $2.5 and 20 minutes headway. So that means our optimal solutions keep FRT cheap and more frequent to provide the capacity benefit, and it uses the microtransit fares to manage the demand, and also through the fares it helps improving the cost recovery. In Lemon Grove, we also see that the optimal solutions use per trip subsidy quite higher, that is $21 to $40. Whereas in downtown San Diego, we see that the per trip subsidy can be negative as well. It goes from -$3 to $11. So we can say that microtransit productivity and cost recovery depends on context. That means demand or the FRT service currently available. In suburban Lemon Grove, higher mobility improvements come with high subsidy investment, whereas in downtown San Diego, we can have mobility improvements actually with lower subsidy investment. So we introduce a bi-level optimization framework with simulation-based modeling. Then we provide Pareto optimal designs for integrated transit system, considering critical objectives. We show that naive designs such as using flat fares for these services actually is very much suboptimal, or the Pareto optimal solutions significantly outperform these solutions. And we also show that the importance of fleet size and all the differential fares that we considered for our design. Thank you.
Great, thank you. About 15 minutes. So, okay, there's a question. You can read it in the chat box, but I read it out for
What
everyone.
was your assumption for access to private vehicle resort?
Okay, I read it out for the audience. What was your assumptions for access to private vehicles? Microtransit has been shown empirically to be used more as a standalone mode for local travel than for accessing fixed route transit. Adding elastic demand and active modes may be interesting.
Yeah, so our assumption for access to private vehicles is that we assume that all the riders in our demand set is having access to private vehicles. So that is one of our future research direction to introduce disadvantaged population which do not have access to private vehicles.
Okay. Any other questions from the audience? Did you consider shared micromobility vehicles?
No, we did not consider them. You might mean the scooters or something like that.
There's another question. Do you consider taxi as a microtransit?
No, microtransit vehicles are usually smaller vans with 6 or 7 passenger capacity, and it is usually managed by a central operator. It is much like ride sharing systems like Uber or Lyft.
But when you say 6 or 7 person capacity, was there sharing in your model to
Yes, yes,
clarify
right.
that?
Pooling involved.
Pooling,
Yeah.
yes. Great. Okay, very interesting results, or a study basically.
Thank you.
Okay, and what about ride-sharing taxi?
Uh, what do you mean by ride sharing taxi?
Yes,
Like,
those are right question in the chat box. If you could please elaborate and be more clear about your question, I would appreciate that.
do you mean
And
if we consider the existing Uber or Lyft services that are there in the region? I don't know
Tiffany,
what
if
you
you
mean
want
by
to
shared taxi.
unmute yourself and ask your question, go ahead and do that. Or otherwise, we probably have to move on in the interest of time. Okay, seems like they got the answer. All right, thank you. Thank you, Ritun, for the presentation. Yes, the next presentation is by Mohammad Mehedi Hasan, who I believe sent a recorded video. Mohammad is a PhD student in civil engineering at Florida State University. His research focuses on public transit ridership, travel demand modeling, and data-driven methods for understanding transportation systems.
Good morning, everyone. My name is Mohammad. I'm a PhD student from Florida State University. Today, I'll present our study on how service supply, frequency, reliability, fares, and COVID are associated with bus transit ridership across Florida agencies. This study provides an overall understanding of how this relationship, and this is not yet a fully developed analysis, so I believe the results should be interpreted as an association that can help these decision makers to identify some of the areas that can be improved. So first, I'll briefly introduce the research problem, objectives, literatures, and the data set. Then I'll explain the methodology and present the main results. And then I'll conclude with some policy implications and future research. So it's important to understand why public transit is really important and why we are concerned about it. Public transit supports accessibility and equity, congestion reduction, and environmental sustainability. But many US transit agencies in the last couple of years have experienced a very declining or an unstable ridership, although it had continuous population growth and an increased amount of investment. So this study evaluates which service and operational factors are most strongly associated with the changes. Here we can see the ridership trend. The figure shows population and transit investment increased over time, but ridership did not grow proportionally. So it suggests that investment only investment may not increase the ridership, but the amount, frequency, and reliability of service are also very important. Also, public transit can reduce automobile dependence, fuel consumption, congestion, and transportation emissions. Many of the report shows how public transit can help improving the environmental sustainability. So understanding ridership decline is important not only for transit agencies, but also for our broader environmental and social goals. So previous studies have evaluated service supply, fares, reliability, and many socioeconomic factors. But most of the studies compare the systems operating under different state policies and institutional environments. But this study addresses this limitation by evaluating 14 different agencies within a single state under a relatively consistent state-level context. So here comes the main objectives of the research. The main objective is to identify the important determinants of bus ridership and to estimate service and fare elasticities, assess the COVID-19 impact, and test whether the main findings remain consistent across different models. The final objective is to translate the findings into a practical guidance for the transit agencies and stakeholders. Now I will briefly review some of the recent literatures. So previous research shows greater service supply and shorter headways generally support ridership. Reliable operations are also important because failures and delays can reduce passenger confidence. Higher fares usually reduce the ridership, although it varies across different transit systems. Then socioeconomic and land use conditions also influence transit demand, and COVID-19 created a major external disruption, which later initiated remote work and changed the travel behavior. So we identified the main gap among various literatures that there are only a very few research actually jointly examine all the factors across within a single state and within a consistent regional settings. So in this study, we will basically analyze the factors that affecting the ridership in a similar environmental context within a single state. So this study used the annual agency level data from 2008 till 2023, which is obtained from the INTD website database. And this study uses 14 major and medium-sized Florida bus transit agencies. We used the annual ridership as the main dependent variable, and the main explanatory variables include vehicle revenue hours, headway, failures per trip, operating speed. We have effective fare, population density, and unemployment. We also included COVID-19 and the linear time trend. So the main model here is an agency fixed effect panel regression. It actually evaluates the changes within each agency over time, and by controlling the permanent differences among the agencies, such as geography, network structure. We have time trend. Time trend captures gradual system-wide changes, and COVID-19 indicator captures the pandemic disruption. We also did robustness check. Two alternative models were estimated. We have pooled OLS that provides a basic benchmark without the agency fixed effects. The two-way fixed effects model controls for both agency and ER effects. Comparing these two different models actually help determine whether the main results depend heavily on a particular modeling choice and whether our analysis is robust. This is the main equation that presents the main model. The dependent variable is the logarithm of annual ridership. Here alpha represents the agency fixed effect and epsilon represents the main unexplained variation. So the ridership and several explanatory variables are logged. Their coefficients can be interpreted as elasticities. For example, a coefficient of 0.5 indicates 1% increase in the variable is associated with roughly 0.5% increase in the ridership. So this is the main results. Here we can see vehicle revenue hours have a significant positive relationship. I'll discuss the main trends found in the analysis here. So vehicle revenue hours has a coefficient of roughly 0.58, which means a 1% increase in the service supply is associated with roughly 0.6% increase in ridership. The headway coefficient has a negative minus 0.25, means 1% increase in headway is associated with roughly 0.25% reduction in ridership. Similarly, 1% increase in failures per trip is associated with around 0.25% decrease in the ridership. In terms of fare, this is associated with roughly 0.12% decrease in ridership, although it's marginally significant. And then we have COVID impacts. COVID had a great impact on the ridership. The COVID corresponds to the reduction approximately 30% after controlling the other factors. We also have a negative time trend. The negative time trend indicates an long-term decline. By 2023, average ridership recovered around 77% of the baseline level, which is 2019 level. Then we have the results for the robustness check. This table compares the two different forms. We have pooled OLS and we have two-way fixed effects. The numbers here are estimated coefficients, while the stars here shows the statistical significance. The most consistent result concern headway and vehicle revenue hours. Headway remains negative and service supply remains positive and significant in both of the models. Reliability and fare retain negative signs but are more sensitive to the model choice. The COVID variable is not separately estimated in the two-way model because it is actually absorbed by the ER effects. But overall, the central service supply and frequency findings are robust, while some secondary results vary across the specifications. So I want to highlight some of the major findings. Service supply is the strongest positive determinants of bus ridership, while longer headways and more service failures are related with lower ridership. Fares actually matter, but service-related factors seems to be more influential. COVID-19 caused a very huge impact. It was a major disruption and recovery remained incomplete by 2023. During our study, we had actually had the data till 2023. So our study analyzes the period till 2023. Agencies that want to build the ridership, so they should prioritize actually the sufficient service, shorter waiting times, and reliable operations. This is one of the key findings from our analysis. And the future research, it could include some relevant topics such as the impact of telework, emerging mobility, and it can also include a detailed demographic and land use information. A route level analysis or some short-term changes analysis can be also done, and it can be extended to other states and other transit modes. So to conclude, the studies actually shows the service quantity, frequency, and reliability remain very important to bus transit demand, even during a period affected by major external shocks like COVID. So thank you so much for your attention, and I welcome any comments, and I wish you have a wonderful rest of your day. Thank you.
Okay, Anandya, thank you for sharing the recorded video. If anyone has any questions, please feel free to reach out to Mohammad, the presenter who sent the recorded video directly. We are moving on to the next presentation by Saurav Pokharel. Saurav is a third-year graduate student at the University of Arkansas. His work involves understanding the travel behavior of people in different modes, like transit or shared micromobility. Currently, he's working on understanding food accessibility in the state of Arkansas. Saurav, go ahead. We can see your slides, and yes, go ahead.
Hi everyone, just give me a moment. Can you see my slide?
Yes, we can see it. Okay.
Hi everyone. As our session here already introduced me, so today I'll be presenting you one of my work that is on public transit. So the topic is the 2 decades of change in the US public transit uses, and we look into the trends, determinants, and the post-pandemic shift. This work was supervised by my supervisor, Dr. Suman, Mitra. So before moving towards the presentation, I'm giving you the outline of the presentation. First, I'll talk about the background, then about the data, and similarly towards methodology, results, and finally, we'll talk about the policy implication. Let's move into the background, why we need to analyze public transit uses. We all know that public transit is one of the great means of urban mobilities that helps reduce carbon emission and provide a sustainable means of transportation as well as affordable means. And similarly, understanding public transit uses is not just looking into the ridership directly. So several other factors influence public transit uses, such as economic fluctuation, demographic shifts, advancement in other technologies, and even like the COVID-19 pandemic as discussed by the previous presenters. So all these factors are important to analyze the public transit uses. Let's move to the next slide. That is why we need to understand transit trip characteristics and socio-demographic factors over different time periods. So understanding the transit trip characteristics help us know why and how people use transit over different time periods. Similarly, understanding the socio-demographic composition helps planners and agencies to access how these characteristics of transit ridership evolves across different time periods. These things are crucial for identifying trends so that we could directly implement in terms of policy. Now let's see about the current state of transit study across different years. Mainly the literature are divided into 2 major sections. The first section talks about the transit ridership relationship with the transit fares, gas price, and the transit frequency. And the time frame for most of these studies are from 2002 to 2018. That is right before the COVID. And then the maximum number of cities that these study include in one particular study was the maximum of 25 cities, that was including US cities and Canada. And the other section of the literature talks about the relationship between the public transit and the socio-economic characteristics. However, in this section, the literature mostly they are confined to lower number of cities. And one particular studies has studied about 4 cities to understand the public transit uses, and the time frame most of the literature are from 2012 to 2018. So what's the research gap that I'm trying to address in this study is most of these studies, like the single study, they didn't focus on the trip characteristics over multiple time period. And the another one is, which I have already said, that these studies, transit studies, they are particularly confined to cities or agencies, and we do not have a better representation on a national level. And there is no inclusion of the recent time data. And the major thing is there are several studies regarding transit uses during the COVID time period, but one particular study that did not compare the result transit uses before and after the COVID period of time. So this led to the objective of my studies, and here are the objectives listed here. The first one is to analyze the changes in the transitive characteristics over different time period 2001, 9, 17, and 2022. I'll tell you why I choose this particular year. And another one is to compare the socio-demographic of transit users across different years. And finally is to examine and compare the factor influencing the transit uses across these time points. The dataset that I use is the National Household Travel Survey dataset. This is nationally published dataset by Federal Highway Administration in the US. And the reason I'm talking about the use of 2001, 9, 17, and 22 is because these are the years when these National Household Survey dataset were published, and we have information for that particular year. This survey consists of 4 particular files in each of those years, consisting the information about the household, vehicle, person, and the trip taken by the member of the household. In terms of public transit, here is the insight from all different NHTS years, and we could see the ranges. It ranges from 0.73% of transit share to 1.6% across different years. So in our study, I have used the trip file and the person file for this study. We also see that you can also see there is a less number of transit trips in 2022 year. This is because they changed the sampling method. They use the stratified sampling to reduce their travel survey costs. And in order for the representation, they provided the weightage for each of their observation. So during the data cleaning process, we remove all the negative and unidentified values, and then from the trip file, we calculate the number of trips taken by each individual, and finally we merge that trip details into the person level file, and the sampling numbers used for each year is listed below. Similarly, in the data section for the variable of household income category, we created the 3 categories, that is middle income, upper higher income, and the lower income. For the creation of the middle income household, we take the median from the US Census Bureau for each particular year, and to create the category for that one, we use the definition from the Pew Research Center for the middle household income, that is the ranges from 2/3 median income to twice of the median income, and any income categories that lies above this one is categorized at high income household, whereas lower is classified as low income household. We also modified another variable, that is to create vehicle ownership status and we categorize it into the 3 different categories, that is car sufficient, car deficit, and car neutral, based on the vehicle to driver ratio. This one is to understand how these different categories affect the public transit uses. And all other variables were used as specified in the dataset, and only categorization was done based on those values. So let's move into the methodology section. In order to fulfill our first 2 objectives, we use the weighted data analysis. We use weighted because the sampling size and the sampling structure of the 2022. And in order to fulfill these objectives, we use the trend visualization to see the trip characteristics. And similarly, for the socio-demographic, we rely on the data and the proportion of the uses of different categories in each particular year. And to fulfill our third objective, we use the binary logic model, and whoever takes the public transit is categorized as the transit user, that is our dependent variable, and who didn't take the transit were categorized as non-users. And we explain the result of the binary logic model with the help of odds ratio. Multicollinearity was checked for each variable before starting the binary logic model, and goodness of fit were checked with all these log likelihood, AIC-BIC ratio, and some other tested listed here. And finally, to compare the level of significance influencing transit uses across different years, we use the standardized regression coefficient G-test to see how these variables significantly affect the transit use between two consecutive years or not. Now let's move into the result for the objective one, that is analyzing the trip characteristics of transit users across different years. So here you can see the results for the trip distance pattern, that we can see that the percentage of 1 to 3 mile trips were high in 2017, which got reduced in 2022. This could be because of the reduction in the non-essential trips right after the COVID period of time. Similarly, we could see the percentage of 5 to 10 miles trips and 10 to 25 mile trips were low in 2017, which got increased in 2022. This suggests there might be a shift in the changes because of the trip proposed. Let's see the other figure. This one is about the trip duration. Here we can see that the percentage of 15 to 30 minute trips were low in 2009. Some literature suggested that this could be because of the increasing of the urban sprawl, which could lead to the lower shorter trips, and there is a reduction in 2022. This one we conclude because of the pandemic situation. And we could also see that the percentage of the 60 plus minute trips were high in 2009 and 2022. This could be because of the traffic situation in that particular city, or could be the intra-city travel. And here's another result from the trip proposed. We can see that there is a fluctuation of trips in the work trips, and more important, look into the school trip. That is, the percentage of school trips were really high in 2017, which reduced drastically in 2022. There have been several research on the pandemic period of time, and the issue was related to the COVID, and they conclude that it could be because of the COVID and the restriction during that period of time. It has the fewer school trips. And another interesting observation is the medical trip, that is high in 2001, which never reached to its peak afterwards in any of the next year. This indicates that there is a uh, huge gap in accessibility to medical care by the transit system. And here is the time of the day result for each particular year. We could see that the percentage of 6 a.m. to 10 a.m. transit trips were high in 2017, which indicates the traditional commuting pattern. And then in 2022, percentage of 10 a.m. to 3 p.m. transit trips were high. This could be because of the work flexibility right after the COVID period of time, that people are choosing different time period for commuting, I guess. And moving towards the result of the objective 2, that is analyzing the socio-demographic of the transit users across different years, I have presented the major results here. We see that the portion of the female that use transit is more than the percentage of the males using transit, and there is a declining trend in the use of the transit by children who are less than 15 years of age. And similarly, however, there is an increasing trend in the use of the transit by carless household from 2001 to 2022. In 2017, low-income groups were majorly using transit more as compared to high-income groups and middle-income group. But in 2022, this trend changed, and the middle income become the high income, like highest users of transit. And as obvious, MSA area with rail and urban area has increasing transit uses across all in all those years. This is obvious because they have the transit oriented development in those areas. In order moving towards the result of the objective 3, that is the examining the factors associated with the transit users across different years. And here is the result from the binary logic model. The colored variable shows the significant variables. We can see that the sex remains the significant predictor of transit users only in 2001, and age and employment remains insignificant in 2022. Moving towards the key summary of the binary logic model, we can see that in 2001 only the females remain only sex remains the significant predictor in 2001 only. This suggests that after in 2009, 17, and 2022, we couldn't see any gender differences in the transit uses. Similarly, we can observe that the likelihood of the uses of transit decreases with age. Black people are have higher likelihood of uses of transit as compared to other race groups. Similarly, employed individual, middle income, and employed individual are more likely to use transit, and middle and high income are less likely to use transit. And there is also an observation that the car sufficient and car neutral group are less likely to use transit as compared to car deficient group. This one is obvious, and similarly, the MS areas with rail have higher likelihood of users of transit, as already said before. And moving towards the continuation of this third objective, that is to compare the significance level across two consecutive years. Here's the result from the G test. We can see that the vehicle ownership status and the household income remains significantly different in predicting the transit uses between two consecutive years across all these three time period. However, household size remains the significant predictor in determining the transit uses between 2001 and 17, and similarly in the urban case it remains significantly different between 2017 and 2022. To sum up everything, here's the key takeaway.
Please wrap up in the next few seconds. We are already past the time limit. If you want to share the key takeaways, yes.
Okay, here's the key takeaway from these studies. That is the school trips, it reduced in 2022 and never reached to its peak. However, the medical trips were high in 2001, and we couldn't get to that level after so many years also, and we could see the time shift in the commuting pattern. That is, previously it was the early morning, and later on it shifted towards the midday travel, and we couldn't see the gender differences across all these years. And policy implications should be towards targeting the school children with the school passes and partnership to encourage transit uses. And decline in the medical trips from 2001 suggests there is a gap in healthcare accessibilities, and targeted routes and flexible services for these trips is helpful. Finally, the policies are related towards increasing ridership. This would reduce the car dependence and lower the emission and help in creating the sustainable environment. Thank you.
Thank you very much. We can have time for one quick question, and there is one question in the chat box. It's was COVID modeled as a short-term, long-term, or a lingering effect?
I mean, these data set, they are for the particular time period. So the data set that we obtained from 2022 was the right after the restriction were lifted off for the COVID, and these data set were collected. So particularly, we don't have the exact COVID period during that particular time, but the whole objective was to see like how this trend goes along the before and after the COVID period of time. However, there are several other studies that focus particularly on the COVID period of time. Our objective was to see it over a different period of time.
Okay, there's no other question in the chat, and we are going to move on to the next presentation. Thank you, Saurav.
Thank you.
Okay, last but not least, the presentation is by Tudor Istrate, if I say it correctly. Tudor is a transportation engineer and a PhD student at the University of Science and Technology, Polytechnica Bucharest, specializing in public transport planning, network accessibility, and GIS-based analysis. His research focuses on practical, data-efficient approaches to prioritizing urban transport investments. Welcome to Dor, and go ahead and we can see your slides. You're good to go.
Thank you for having me. So before starting the presentation, I would like to thank my coordinating professor, Dorina Costescu, for her feedback and guidance. The study is based on a network accessibility cost framework for investments that seek to prioritize public transport in Romania. And there is also a case study on the Bucharest tram network to showcase the framework. So moving forward, we are currently seeing growing access to funding for public transport projects in medium and large-sized Romanian cities. And to make most of these funds, infrastructure investments require effective prioritization. However, local administrative bodies often operate in data-scarce environments, and this creates basically a strong necessity for a framework that offers rapid solution, flexibility, and the ability to objectively prioritize those projects during early planning stages. Traditional evaluation methods naturally have their disadvantages. So first of all, I discussed about cost-benefit analysis used to prioritize projects. So when discussing about it, in a data-scarce environment, the lack of data makes it difficult to ensure that the results are coherent. CBA applications depend on travel demand forecasts mostly, and these are also based on transport models, which in a local context might not always be available or done. So with that in mind, this raises issue about the best case definitions, the valuation data quality, and sensitivity testing tied to forecast uncertainty, and again bringing in mind the data scarcity in local environments. On the other hand, we have a multi-criteria analysis, which can often provide subjective results when the agents taking part in the scoring process most of the time are also directly impacted by the results, especially on the administrative body side. So going forward, to bridge this gap, our proposed framework requires widely available and easily accessible and preferably open source geospatial data. And I've given an example, OpenStreetMap extracts. The methodology relies on two primary inputs, point-based data set representing locations of public transport stops or stations for the analyzed mode. So and network data set representing the infrastructure used to connect the stops, so links between the mentioned stop points. Next, the methodology follows three subsequent steps. The second one will be generating origin destination cost matrix, utilizing shortest path algorithms to establish a baseline of existing network accessibility. This can be done using software which is mandatory in most administrative bodies in Romania. The next step is scenario testing, which is modifying the network topology by simulating projects or aggregating certain projects into different scenarios. Then the accessibility improvements across all node pairs are used to gauge system-wide impact against expected or approximated implementation cost. And the last step is to calculate the accessibility gain ratio, which provides decision makers with a scalable index for transparent project ranking. And here we can see the formula where the sum of the difference of cost between pairs of stations, so station I to station J, is the sum of the difference between the two scenarios. And the PC is the project cost, which is determined as an approximation based on either on similar projects done in the past or taking scenarios in other cities. I also have put out two disclaimers that currently in the form that I've managed to create the ATR is that the current framework only works for same mode analysis, and that distance in the context of the case study is used as a metric intentionally to demonstrate the framework under minimal data requirements. So taking a look at the framework, the flow chart illustrates the overarching architecture of the proposed methodology. In the baseline, the base scenario, the process begins by mapping existing tram stops and the network to generate the cost matrix, the origin destination cost matrix. Then we analyze the project. So by discussing with the stakeholders, we then would get the project roster, and we would group projects based on their impact in different scenarios. Then by quantifying the matrix cost of the scenarios in itself, we get different scenario matrices, and these would then be compared to the original baseline matrix. By modifying the cost, we would then compare the different accessibility cost matrices to each other, and then generate the AGR with taking into account the project scenario for implementation cost. While being intended for early stage screening, where budgets are mostly unavailable, the idea is to utilize generalized cost approximations. So to establish a project's financial value, we analyze historical data, as I said, from past projects that share similar scope, length of network, and even placement. So by extracting this economic data, we can derive generalized unit costs per kilometer, and as such, find out at least an approximate cost for each project and then scenario. And finally, we bring these two metrics together by dividing the total network accessibility gain to the project costs, and then as such getting the AGR value. So moving forward with the case study, to exemplify the framework, we applied it to Bucharest tram network. The system spans over around 290 kilometers with 22 active lines stretching for the most part of the city. However, the network experiences severe operational friction due to mixed traffic conditions. So we have private car use on the tram tracks. And a critical point would be the lack of a transversal connection through the city center. So it's mostly radial, and we cannot transverse the city using tram. So using the model network, we generated the baseline matrix containing the distances between 269 stations, which then results a total of 72,630 values. By aggregating those values, we also identify three main hubs, which have the lowest cumulative travel distances, and they're quite similar, and we can see a definite point towards the center of the city, so near the center of the city. The top 3 main hubs are the ones that follow in the table. Moving to the next stage of the baseline evaluation, the accessibility analysis, as I said, clearly showcases a gap in the center of the city. And the primary deficiency lies in the transversal connectivity. This absence creates a severe discontinuity between major transportation corridors located on the north, south, and west-east axis. Ultimately, this lack of cohesion reduces the competitiveness of the tram network compared to the one such as metro. Taking this into account, the proposed action would be a very small connection in the center of the city, and this would be the intervention that is analyzed using the framework. So, as I said, the network intervention was modeled through the center plaza, and the post-intervention matrix captured the structural shift, showing an overall network accessibility improvement of 9.2%. And as an example, one of the hubs mentioned before singularly had an impact of 13.7%. The overall network accessibility improvement, representing the sum of the difference of the cost between stations, is 70,129. And to estimate the costs, we used recent tram reconstruction projects in adjacent areas, resulting in a unit cost of 8.81 million euros for the intervention per kilometer. The number might be huge, but we should also take into account the historical side of the area and the multiple architectural interventions that require to be done for the intervention. And by calculating the accessibility gain ratio, we gain an efficiency of 8,843 kilometers per million euros invested. Okay, so as a conclusion, the appraisal framework proposes a streamlined network-based methodology, bridging the gap between resource-intensive cost-benefit analysis and a subjective, maybe subjective MCA. It is efficient and reproducible by using very simple GIS network analysis and widely available geospatial data. As seen in the case study, we can easily calculate a metric for a simple intervention. And the AGR relates total accessibility gains to implementation cost, as such providing a transparent indicator for comparing investment alternatives. And going forward, we define future areas for improvements. While the methodology can be highly effective for early stage screening, there are definitely several important directions for future refinement. Firstly, we aim to position the accessibility measure more firmly within the broader literature. While distance was used here to demonstrate the framework under minimum data requirements, we plan to incorporate variables like travel time, generalized costs, service frequency, and transfer penalties to better reflect the true passenger experience. Next, where data is available, we plan to introduce passenger demand weighing to ensure that the framework favors projects serving the greatest number of users. And finally, we intend to validate the framework across different public transport projects and even aggregating into scenarios and seeing if that context changes. So thank you for your time and attention. And if there are any other questions.
Thank you. Great presentation. We have time for some questions. If anyone has a question, please type it in the chat. I had one question that you kind of answered on the last slide, and that's about the demand, whether the accessibility metrics are weighted by demand. I think you kind of mentioned in the future improvement that introducing demand weighting. But let me elaborate that a little bit more. First part of my question about the demand weighting, if you want to comment on that. The second part is that when we weight by demand, then would it be a better idea to use a different accessibility metric that is not exactly just travel time, because people may have user behavior that they may prefer more direct routes, avoiding transfers, or may have different weights for in-vehicle time, waiting time, and so on?
Yes. So thank you for the question. On the first part, yeah, of course, demand weighting is important, and it's necessarily implemented where it is available. And to go to the second part, in my experience working locally, where this would have a good implementation place, such data is not readily available, and it would be gained later on in the project stage. And by that point, maybe a CBA analysis would be better fit to analyze the impact of the project. So the framework that I propose is placed much earlier than a CBA would be reasonable to use. And when CBA data becomes available, then yeah, of course, then this framework is not suitable for this application.
Okay, thank you for your explanation. There was a question in the chat. Weighting by local population unemployment can inform effect of service into currently unserved areas, if I read it correctly. Is that a question or comment from Robert?
So I agree.
Yes, that's a great point. I mean, but weighting by population employment, at least it shows the potential for the system being used by people. It doesn't show exactly how much demand is using the system, but it shows the potential at least.